Good afternoon, everybody, and welcome to the Lesaffre UK and Ireland webinar on the subject of liquid yeast systems. Thank you very much for joining us today. Before we begin, we have a few housekeeping messages for you. You'll get the best connection to this webinar if you're using the Google Chrome browser. Please could you make sure that there are no other applications open on your device that you're using that have a microphone or a camera attachment, and please ensure that any microphone that you might have attached is muted so that it prevents any ambient noise that might cause feedback. And finally, we should be having a questions and answers session at the end of this presentation, so please post your questions using the chat function at the side of your screen or the questions box. And please post to moderators only to preserve your own anonymity, unless you don't mind knowing who it is who's asking the question. And always, as always, if there are any questions that we don't get a chance to answer today, we'll send you an answer by email. You'll also have a chance to revisit this presentation later on, as we shall be posting it on our YouTube channel. Just type Lesaffre UK into the YouTube search box and you'll find it there, along with all of the other webinars that we've presented throughout this year. So now let me introduce our speakers. My name is Sara Autton and I'm the Technical Manager at Lesaffre UK and Ireland. And I'm joined today by Mark Beattie, who is our Technical Support Engineer for Creamiest Yeast Systems. He assists in the design and management of our cream yeast installations and is also responsible for customer support post-installation. Welcome to you, Mark.
Good afternoon, everybody.
And we're also joined by Monika Webb, who is our Quality and Audit Assistant Manager, and she is responsible for the liaison between the quality departments of all our yeast manufacturing sites in Europe, who supply all grades of yeast through Lesaffre UK and Ireland, whether cream or dry or compressed. And she'll be telling us something about these later on. Welcome to you too, Monika. Thank you for joining us.
Thank you, Sara, and hello.
And I must also mention Gulten Yagmur, who's managed the process of putting this presentation together and sorting out all of the technical issues. So thank you for your very important work in the background, Gulten. So to begin with, let's just remind ourselves about yeast, what it is, what it does, and how it's made. So yeast is a living organism, and like all living things, it needs certain requirements to maintain its health and viability, which need to be respected in order for it to function properly. It's a very simple organism, unicellular in form, and it's spherical or oval in shape. It's a very small organism, only a few microns in size for each cell. There are many different strains of yeast, but the one that bakers are most concerned with is this one, Saccharomyces cerevisiae. And this name derives from its origins. It feeds on simple sugars, hence saccharose. It is classified as a fungus, myces, and this particular strain was originally used for the fermentation of beer, probably by the Sumerians some 8,000 years ago, hence cerevisiae. And here you can see a block of yeast as it appears under extreme magnification. The photograph on the right of your screen shows individual yeast cells, and you may notice that some of them have bumps on them. And these are cells that are in the process of budding, which means that they are reproducing daughter cells by an asexual process, which means that each cell is an exact clone of its mother. Other cells that you can see in this photograph have dents in their surface, and those are the scars that are left behind once the daughter cells are split off. Given the correct conditions, each yeast cell can produce around 20 daughter cells before its surface is too scarred to allow for any further reproductive activity, although the yeast cell itself can still ferment and produce carbon dioxide. Yeast is capable of existing both with or without oxygen, having different activities depending on whether its environmental atmosphere is aerobic or anaerobic. Where there is oxygen present in aerobic conditions, yeast enters a respiratory phase, where it consumes sugars and uses its energy to reproduce by budding. On the other hand, if there is no oxygen present, i.e. anaerobically, the yeast enters its fermentation phase, and this is the property that bakers exploit in their bread making processes. In this instance, there are two aspects of fermentation. Firstly, the main function, where the yeast metabolizes glucose to produce carbon dioxide, and which is needed to make the dough rise. And this is an exothermic reaction, producing heat, which is why the dough temperature also rises during bulk fermentation and proof phases of the bread making process. The secondary fermentation function, involves the breakdown of glucose to form the organic acids and other compounds that are the precursors for bread flavor and aromas that we all know so well and with which we all tempt our customers. So now that we've reminded ourselves of what yeast is, let's have a look at how yeast is made. As I've already mentioned, yeast requires specific conditions to survive and remain active. When we produce yeast on a large scale, Lesaffre carefully controls all of these various conditions needed to ensure the health of the yeast cells during reproduction and the fermentation performance of the finished yeast that's supplied to bakers all around the world. Key amongst these controls is the scrupulous attention to hygiene, which is essential to prevent any contamination with unwanted microorganisms. After all, we're giving the yeast the optimum conditions for growth, and we need to remember that these are also optimum conditions for the growth of some microbes that we don't want in our yeast. There are two main stages of yeast production. The first is conducted in a laboratory, and the second is the main industrial stage, which produces the bulk of the biomass of the yeast. Let's have a look at the video, which shows some details of the process from the beginning.
Here at Lesaffre, we are experts in the fermentation of yeast. Fermenting means organizing and controlling the environment while providing high-quality yeast cells with the materials they need, like sugar and oxygen, for example, in order for them to generate many other cells. At Lesaffre, we create all the right conditions for fermentation, enabling the yeast cells to multiply. Let's learn how. It all begins in what we call the strain bank, where the different strains of yeast cells are stored at -80 degrees Celsius. An initial liquid culture is prepared in a tube. A few milligrams of yeast are transferred to a culture medium, and this is placed in an incubator at a favorable temperature. The fermentation process then requires patience. Next, the yeast cells are transferred to a larger environment. The purpose of these different stages is to successively increase the biomass, namely the quantity of cells produced, in order to reach a sufficient quantity of yeast. We can then pitch a fermenter to obtain the first generation yeast. The end result is several tons of yeast generated in just a few days. The yeast is then separated from the culture medium, which enabled the cells to multiply thanks to the use of a centrifugal separator. This gives us a cream, which is then cooled and stored in chilled conditions at 4 degrees Celsius to ensure that the yeast cells are inactive. In this form, the yeast can be processed in order to be sold. At this stage, it can already be sold as liquid yeast by preparing just the cream yeast. This liquid yeast is then sold in three forms, either in Castalia, which is a sort of refrigerated bag, or else the cream yeast is sold in a container 0.1 to 1 cubic meter, or in 25-ton trucks for very large bakeries. We also market another type of yeast, namely fresh or compressed yeast. The yeast cream is passed through a rotary filter, or vacuum filter, a machine which sucks away the liquid, making it possible to obtain a fine layer of yeast. This layer is then processed in a mixer, which compresses the yeast. Next, the compressed yeast is cut into cubes and packed. To obtain dry yeast, namely dehydrated yeast, the yeast cream passes through a rotary filter once again, but then goes into an extruder and a drying plant, making it possible to remove even more water from the yeast layer. And that's how we make yeast.
I'm sure that you noticed that all formats of yeast originate from cream, and cream yeast systems are the focus of our attention today. So now I shall give the floor to Mark Beattie, who will describe the various equipment installations available to handle liquid yeast in different bakery settings. Thank you, Mark.
Thank you, Sarah, for that informative introduction. And good afternoon, everybody, and welcome to my part of the webinar where I'll be discussing liquid yeast systems. Okay, so in terms of liquid yeast systems, we can see from this slide there are a number of different options we can choose from. We have the bulk yeast system, which is delivered by road tanker, typically in the range of between 5 to 25 ton of yeast. We have our 1000 kilo container systems, which utilize stabilized yeast. We have our 300 kilo container systems, which also use stabilized yeast. And finally, the Castalia 22 kilo bag-in-box systems, also using stabilized yeast. Okay, before we discuss each of these systems in a little bit more detail, let's first examine some of the pros and cons of liquid yeast. Firstly, liquid yeast systems are a very hygienic way of using the yeast, meaning it can be pumped directly to the mixer without any human contact or the potential for any contamination. Secondly, these systems operate with a very high degree of accuracy. Utilizing modern flow meter technology and fast-acting dosing valves, excellent levels of accuracy can be achieved time after time. Yeast when you need it. One of the negatives of using compressed yeast is the need to regularly bring it in from the cold room. Quite often, this is done in significant quantities to see the operator through numerous mixers without the need for constant traipsing to and from the cold room for more. The problem with this is, not only does it open up the risk of contamination, but also the yeast can be sitting for a long time in a warm environment, and as the yeast increases in temperature, it will start to become active long before it's used, potentially impacting its performance. Temperature control, another important factor. The yeast is kept at its optimum temperature of around 2 to 4 degrees, meaning we can be confident of its performance in the mixer when it's needed. We have improved dough consistency. Due to the yeast being in liquid form, this means it can disperse in the dough more easily and often result in lesser quantities being needed than with conventional blocks. Packaging costs are saved. As you can imagine, if a bakery is using, say, 5 ton of block yeast per week, that means there will be 5,000 individual wrappers to dispose of, not to mention the boxes that they were stored in. Using liquid yeast does away with a lot of this cost and inconvenience. And finally, data logging. This is an extremely useful tool and gives access to a wealth of data when needed, such as dosing logs, temperature trends, daily usage, cleaning logs, etc. Okay, so let's look at the disadvantages. Capital cost of the equipment is probably one of the major downsides. Yeast systems can be a large expense, but can actually pay for themselves in terms of efficiency improvements quite quickly. Plus, they do last a very long time if they're looked after properly. System maintenance needs to be considered. The plants do generally look after themselves, but nevertheless, preventative maintenance needs to be factored into production schedules. Larger yeast systems, particularly the bulk plants, require a little bit more in the way of skilled staff to operate them. They are very simple to run on a day-to-day basis, but certain tasks, such as cleaning, taking deliveries and managing repairs, do need to be considered. A weekly 2-hour cleaning window needs to be factored into production for cleaning the pipework. This can be done on a shutdown day if one is available, or even during production if there is a small amount of yeast available to keep the mixers going. Increased energy costs, water usage for cleaning and power for the day-to-day operation will be slightly increased. And finally, space taken up by the plant is an important factor in a lot of bakeries where space can often be at a premium. So moving on to individual systems then, let's start with the smallest of our systems and work our way up, beginning with stabilized yeast in the form of Castalia. The Castalia system, as you can see here, is a really good introduction to the world of liquid yeast and offers numerous benefits over traditional compressed yeast blocks. 22 kilos of yeast is packed into a breathable bag, which is then placed inside of a cardboard box. A dedicated refrigeration unit is provided by us that allows the safe and ideal storage conditions for the yeast and also as a means of dispensing it. Okay, so in this slide, in the first image, you can see that the box sits inside of its own fridge unit, which in turn sits on a workbench somewhere in the bakery. A special nozzle is fitted to the underside of the box, which allows the yeast to be dispensed into a jug via this lever. The yeast can then be weighed off and manually added to the mixer. Unfortunately, with Castalia, there is no means of automatic dosing, but it's a very useful addition for a small craft bakery. It's also a very good way of trialling liquid yeast when considering a larger system. The next system to mention then is the 300 kilo container system using stabilized yeast. These are for small to medium-sized bakeries where weekly yeast usage is around 200 to 500 kilos approximately. However, this can vary with other factors, and this system is actually often used in addition to using compressed yeast on another line. So the 300 kilo container, as we can see here, is on wheels, meaning it's easily transportable and maneuverable. And these containers, like the block yeast, need to be stored in a cold room somewhere in relatively close vicinity to the mixer. The container has a basic level system, which alarms once it's near empty. This informs the operator to switch to a new container, at which point the old container is replaced and the empty one stored ready for collection upon the next delivery. The container also has a rudimentary vent on top to allow the CO2 to escape and to prevent any gas buildup inside the container. The outlet is at the bottom of the tank and is controlled by a manual butterfly valve. From this outlet we connect to a length of hygienic hose, as you can see here, which then feeds a small air-operated diaphragm pump. This pump discharges the yeast through an inline filter and then out through the cold room wall into the bakery. As you can see here, there is no means of returning the pipework back to these containers, meaning they are one way out only. And as such, the usage and the length of pipework does need to be considered to prevent yeast in that pipework from heating up too much. If the system is going to be left unused for any length of time, particularly more than an hour, then the pipework should really be flushed of yeast with water. There are a couple of ways we can dose the yeast. On the right hand side we have a pneumatically operated push to dose system. Very simple. Place the jug under the spout, press the button and dispense the yeast into the jug, which can then be weighed off and added to the mixer by hand. On the left we have a slightly more sophisticated system in that we're using a panel with a flow meter and a dosing valve. This allows the accurate dosing of yeast into a jug or even directly into the mixer. Obviously, the system on the right is the cheapest and easiest option. Moving on then, the next system to discuss is the bigger version of the 300 kilo system, the 1000 kilo system. So on this slide you can see a typical 1000 kilo container system setup. The two containers sit side by side with the pump skid in the middle. The pump is shown at the bottom. They are stored in a cold room. You can't quite see it on this image, but they are in a cold room. And they differ in how they look to the 300 kilo systems in that they're not on wheels, so they do need to be moved around via a forklift truck or a pallet truck. The other very important factor with the 1000 kilo systems is the addition of a return inlet on top, as we can see here. Because of this top return connection, it means that these containers can now be used when a longer pipe run is needed inside the bakery, or even to feed multiple mixers. The thing we need to consider with pipework, of having more pipework in the bakery, is the potential for it picking up any residual heat. This could result in the yeast increasing in temperature and becoming active. Therefore, to prevent this happening, the yeast circulates periodically back to the container so that it stays at its optimum temperature. The pipework is also insulated, which can prevent temperature increases for approximately 1 hour. The pipework loop that you can see here is what is termed a ring main. These systems typically also use a bigger pump than the 300 kilo container systems, meaning we can pump further from the cold room up to around about 150 meters or so. A 300 kilo container system would be limited at around 15 to 20 meters. This kind of system is what we would call a manual changeover system. As the container on the left empties, the level probe inside of the container causes an alarm signal to sound in the bakery, which informs the operator the tank needs to be switched over. The operator must then go to the cold room and disconnect the hoses from the empty container and put them onto the new one before the system can be reused. This takes between 5 and 10 minutes. These plants do need a weekly clean down, and as such they come equipped with an integrated wash tank, which is shown in the middle here. This can be filled with a cleaning solution which is then circulated around the pipework for approximately 20 to 30 minutes before being disposed of to drain. The cleaning process does require some manual intervention, but should take no more than about 45 minutes to an hour or so once you're familiar with the procedure. The next system up from this would be the automatic version of the plant. This is a much more sophisticated plant, and as such is geared more towards bakeries that would be looking at regular container changes of around once a day or sometimes even more. The system works in much the same way as previously, but comes with a number of automated valves rather than manual valves, and a number of different sensors as well. When a tank is detected as being empty, then the valve sequence changes and the system automatically switches over to the new tank. An alarm is triggered in the bakery to notify the operator of the change. The controls on these plants are much more in depth and also allow for the automatic cleaning, meaning around 99% of the human interaction that we saw previously is taken away. The plant also logs any key data at the end of the clean for inspection. Now let's look at bulk systems. Bulk systems rely on yeast delivered by road tanker. So when we think about bulk systems then, this is the kind of plant we tend to think of. However, they do vary in terms of their layout and size and also how they're controlled. But generally their functionality and how they operate remains much the same. These systems have been around now for a number of decades, and so how they were designed and how they operate is based on the practices and the technology available at the time of that particular installation. For example, there are still plants in the field today which are entirely manual, offering virtually nothing in the way of automation or monitoring. And then there are plants such as these which utilize something called a flow plate. As you can see here, the flow plate has a number of different bends on it. The position of each of those bends determines the route of the yeast or the cleaning fluid at any particular point in time. These plants are considered to be semi-automatic, meaning they still rely on a lot of operator input in changing those bends, but they do offer some basic automated sequences such as tank changeovers and some cleaning procedures. But importantly, they can offer a much higher level of monitoring too. Finally, we have the fully automatic systems. 99% of new installations will be fully automatic, and utilising something called mix-proof valve technology, we could take full control of every aspect of the plant, whereas in previous generations of yeast plant we would have found this very difficult to do. As you can see on the left, we have two typical screens, and using the touchscreen panel in the middle, we could control individual valves, stop and start different sequences, and have access to a whole number of different logs and data to scrutinize if there is an issue. So as you can imagine, the older plants that I discussed are becoming increasingly more difficult to look after as time goes by. This is mainly due to the availability of now obsolete spare parts, but also in a big way due to the ever-demanding hygiene and environmental standards that we've come to know in recent years, such as those from BRC, AIB, and all of the main supermarket chains, as you can see here. However, with the replacement of certain components within an old plant and the addition of extra instrumentation such as conductivity meters, better flow meters, flow switches, modern control panels, etc., we could bring the plants more in line with the current standards. So looking at these images here, we can see how different generations of technology have advanced in one of those areas. All three of the panels on the right control flow plate systems, as you see here on the left. The older BFP panel in the top right offers little in the way of data monitoring other than tank temperatures, ring main temperatures, tank levels, and some very basic alarm functions. The panel with all the switches in the middle offers more in the way of control and more alarms, but it's still lagging and actually relies on all of those bulbs behind each one of those switches being in operation for it to be of any benefit. Plus, to the untrained eye, it's not exactly user-friendly to work with. And also, there are any number of components in that cabinet that could fail at any given time. The panel at the bottom right does everything the other two do, but also has a much more interactive means of operation and a more sophisticated method of safeguarding. So we can prevent sequences from beginning if bends on the flow plate are not in the correct position. It also has an extensive alarm list plus numerous data logging abilities, as we can see on the next slide. And here we can see just a handful of the data that can be stored within a modern system, such as dosing logs, trending, CIP logs, all the kind of things that auditors like to see. Okay, so let's start to have a look at some of the features of a typical modern bulk yeast installation, and we'll start with the yeast tanks. There are numerous things we could discuss when it comes to yeast tank design, but just to highlight a few. Tanks can come in various shapes and sizes, but generally, as we see here, of the upright cylindrical variety on 3 or 4 legs with a conical bottom. Horizontal tanks are also used occasionally, but are less common and generally for smaller plants or where height is an issue. Tank capacity is a very important factor, and as such should be based loosely around your weekly consumption. So for example, if the bakery is using 20 tonne of yeast per week, we would recommend installing 20 to 25 tonne tanks. These tanks are what is known as jacketed tanks, and they're constructed in 3 layers. We have an inner layer, a middle insulating layer, and an outer protective layer. The middle layer contains a material such as rock wool and also the cooling pipes from the chiller system. It is these cooling pipes that spiral from the bottom of the tank up the height of the tank, which help keep the yeast at the correct temperature. The next thing to mention then is agitation. Bulk yeast systems rely on the continual rotation of an agitator shaft with its attached blades or paddles to keep the yeast in suspense, as you can see here. This is to prevent it from splitting or separating back to yeast and water, which can actually start to occur in as little as 24 hours. It's therefore very important that we rotate the agitator at the correct speed. If it's too slow, then the agitation is not vigorous enough and you risk separation. However, if it's too fast, we can create a vortex in the yeast, as you might see when you drain a bath full of water. This would have the effect of pulling air through the central column of the vortex and into the pump, which would cause something called cavitation. This would rapidly reduce the lifespan of the pump. Therefore, it's essential that we size the motor and the gearbox, as you can see here on the left, accordingly, or use some kind of speed control system. Okay, moving on. The next important thing to discuss then is cooling. Yeast needs to be kept at its optimal temperature of between 2 and 4 degrees in order to maintain a kind of hibernation state. And to do this, we need to rely on a dedicated cooling system. So we utilize chiller units such as these we see here on the left. Like the yeast tanks, these come in various shapes, sizes and capabilities, but generally speaking we would spec the chiller units so that one unit can meet the full cooling requirements of the plant. However, due to temperature being such a critical factor in maintaining the quality of the yeast, we would always install 2 units so that the workload can be shared and there is always one available should one fail. Another factor is when the yeast is in the tank, it's kept nice and cold, but as soon as it leaves on its journey around the bakery, then it's susceptible to picking up residual heat from the warm bakery and also from any friction generated by the pump as it rotates at high speed. So a very good idea is also to install some kind of cooling as the yeast returns back to the tank. And as we see here on the right, we have a ring main return cooler. This could also be a plate heat exchanger. But whichever method is chosen, it means the yeast returns to the tank at approximately the same temperature as that it left. So definitely a very useful addition to the cooling system. I just want to touch on the topic of valves briefly because they do play a very important part in plant design. In older plants that we've seen previously that utilize flow plates, these systems rely heavily on the use of butterfly valves throughout the plant. These are inline valves that open and close to allow or to block fluid flow, and the route of that fluid, be that yeast or water or cleaning solution, depends on the accurate positioning of the bends on the flow plate to ensure that it travels through the correct set of valves towards its final destination. Fully automatic plants use something called mix-proof valves, as you can see here on the right. Mix-proof valves are now much more readily available, they're cheaper, they're easier to maintain, and therefore much more cost-effective than they were 20 years ago. And what they offer over conventional butterfly valves is the ability to have 2 different fluids passing through one valve simultaneously. This means that in a carefully designed system, the same valves can be carrying a potentially harmful cleaning fluid and yeast at the same time without any risk to safety or any risk of cross-contamination. This means we can use less valves and don't need to rely on the use of flow plates. It is mix-proof valves which allowed the jump from previous semi-automatic systems to now modern fully automatic systems. Moving into the last couple of areas now then, yeast dosing. Yeast dosing can be done in one of 2 ways. On the left we can see examples of some dosing panels. These panels allow the operator to take full control of the yeast dosing. They allow a desired quantity to be keyed in, and when the yeast is needed, a signal is sent to open the dosing valve, and utilizing a flow meter, as we can see here on the right, the correct amount of yeast will be dispensed into the mixer. The beauty of independent dosing panels is you have full control of the yeast, and also you have access to logs showing dosing history going back numerous mixes. Or if preferred, we can give full control to the mixer itself to operate the dosing valve as part of a recipe-based system within the mixer software. This is obviously a much simpler and cheaper method. So the final thing to discuss then is the CIP. CIP, or clean in place, means without having to dismantle anything. This is an extremely important part of any yeast plant. Yeast requires very good levels of hygiene in order to thrive. and Monika will discuss this a little bit more soon, but I just wanted to touch on the equipment side. A typical CIP system, as seen here, is a 2-tank setup and comprises of a freshwater tank and a caustic tank. The caustic tank is where a solution of cleaning chemical is made up and stored for the cleaning stage of the clean. The strength of this caustic solution is very important if the clean is to be effective, and so on older systems where we generally had to rely on chemical titration to check the strength of the solution, modern systems use conductivity meters as a means of checking this and are far more accurate. This means the correct strength of chemical is used each and every clean, and additionally we can now check the chemical strength throughout the clean if needed and top up the caustic levels. The caustic solution can also be reused a number of times before it needs replenishing. The third aspect would be the addition of a sanitizer or a sterilant. Usually this is in the form of an acid such as peracetic or phosphoric, sometimes even nitric acid. This doesn't require its own tank and is usually injected directly into the pipework as it's needed via a metered system such as load cells or through a geared pump, as we can see in this image. So there are 2 CIP cycles to carry out on a yeast system. There's a tank clean, which is when a tank goes empty, and there's a ring main clean, which is the pipework. It should be cleaned once a week. The key difference is the tank clean does not affect production and can be done whilst the yeast is still feeding the plant. However, the stages of both cleans are the same. The first stage of any CIP is a rinse through the pipework or the yeast tank with a specified amount of fresh water which goes directly to the drain. Secondly is the cleaning phase, and this utilizes the caustic solution which is circulated from the caustic tank again through the pipework and through the yeast tank and then back to the caustic tank in a continual loop for around 30 minutes. A third freshwater rinse phase flushes away any caustic remnants to drain. And the fourth phase is a sanitization phase using the acid. A predetermined amount of this acid is injected into the pipework and then it's circulated with fresh water for 30 minutes in order to sanitize the system. The fifth and final phase is a freshwater rinse and also known as the final rinse. Quite often though, you may come across a 3-tank CIP setup, and it's this extra tank which allows the final rinse water to be recovered and then stored and then used for the first rinse of the next clean. It's a very good means of saving water. And the last thing to mention then is not all yeast plants use a 5-stage clean. There are chemicals on the market today which allow this to be done in 3 stages. So between the first and the final rinse there would be a 30-minute circulation using a chemical that contains both a cleaning agent and a sanitizer. These are actually very cost-effective 2-in-1 chemicals, but are not quite as good as having the 2 different products. Thank you for your attention. If you have any questions, I will do my best to answer them at the end of this webinar. I hope you found this useful. Thank you.
Thank you very much. Thank you very much, Mark. That was a very detailed explanation. There's a lot of information there. If any of it passed you by, don't forget that you can revisit the presentation on YouTube later on, where you'll find it along with our previous webinars. But if you have any questions for Mark, don't forget to post them in the chat box ready for our Q&A session at the close of this presentation. But that was really very interesting. Thank you, Mark. Now, before we go on to Monika's section, we would like to ask your opinion with a poll. So if you click on the poll icon on the bottom right of your screen, you'll be able to access the question and the answers and register your vote. So we are really interested to know. I promise this isn't a test of how well you've been listening to what Mark has been saying. We are genuinely interested in your views on this question. The question is, what do you think are the most important advantages of a liquid yeast system? Is it the cost? Is it the logistics? Is it the better waste management or the easy handling? So I'll give you a minute or two to vote for your answer. You just click on one of those answers and hit submit vote, and we'll see what you all think. So let's see what you all have to say. So I'll give you a few minutes. And again, don't forget to post your questions in the chat or the questions box at the bottom right of your screen for us to have a chat about those later on. Okay, another minute or two. Okay, I think we will close the poll there. That's very interesting. So it seems that ease of handling is one of the most important, is the most important advantage of the liquid yeast system, which is very good to know. Certainly the business of no manual handling of yeast in a liquid yeast system is very useful from a hygiene point of view, and also for accuracy of dosing. It's one of the things that is clearly very important to a lot of people. Thank you very much for your views on that. So now we're going to hear from Monika as she describes some of the quality aspects of cream yeast and the best ways to ensure that it maintains its functional performance throughout its shelf life, and also some of the applications for the various grades of Lesaffre cream yeast. Thank you, Monika. Over to you.
Thank you, Sara. Thank you, Mark. Hello, everyone. I will talk a bit about Creamiest technical quality, micro quality and quality control during the production process, and a good practice for cream handling in bakeries. Lesaffre yeast quality management approach is to have integrated quality system that covers rigorous selection of raw materials, compliance with GMP, and the application of HACCP methods. Our primary site for the fresh yeast production is based in Ghent in Belgium. The site is accredited to several comprehensive quality and food safety standards. Quality control is a priority. So our laboratories check every batch of yeast for activity, microbiology, and conservation properties. Fermentation activity or leavening power is the most critical characteristic of yeast. It is checked on a regular basis as part of a normal quality control by all bakers' yeast manufacturers. This is done under carefully controlled, constant conditions, which means controlled dough or fermentation medium composition, like a level of sugar or standardized flour, and also under controlled fermentation conditions, for example, temperature and humidity. Liquid yeast has standardized fermentative activity, ensuring consistent performance. The specification of the gassing power in combination with the yeast strain and the production process determine the percentage of dry matter and the density of cream yeast. So the dry matter of cream yeast varies between 15 and 20% of yeast solids, but the cream density will usually be between 1.06 kilo per liter for faster and medium acting creams and 1.08 kilo per liter for slower acting creams. So what are the technical characteristics of our different cream yeasts? Starting with the high activity, this cream is commonly used by industrial bakeries in UK. It is fast acting, suitable for no-time dough, high-speed, short-proof bread and bun production. However, it is not always ideal for stressed dough conditions like high sugar or frozen dough applications, especially where high levels of product consistency are required. So for that, we have a medium activity cream, which has an improved stability under stressed dough conditions. It has enhanced osmotolerance, and it is also suitable for short-term dough freezing. It can provide better flavor potential and improved control of retarded dough. Another yeast we have available in the cream format is freeze-tolerant yeast. This yeast does what it says on the tin, and it is excellent for deep frozen dough production. It is also very good in specialty doughs with slow fermentation, where full flavor development is desired. All these qualities are available as bulk cream or as stabilized cream. As referred in the name, a stabilized cream contains a stabilizer that keeps the yeast solids in suspension and cream homogeneous without the need for agitation. Conversion rates. General conversion rates for high activity yeast would be, for every kilo of high activity block, you'll typically need 1.6 kilo of cream, or if you work in volumes, that would translate to 1.5 liters of high activity cream. For medium activity yeast, for every kilo of medium acting compressed yeast, you will need approximately 1.7 kilo or 1.6 liters of medium acting cream. Flour water hydration will need to be reduced, so the recipe will need to be correctly adjusted to avoid, for example, overproofing or a sticky dough. These conversion rates are not set in stone, so as replacement values can depend on recipes and processes used. Often when switching to cream yeast, bakers see higher fermentation rates during proofing and also increased volumes, product volumes. So cream yeast has high viability due to higher percentage of live cells per gram of dry matter. And this is because cream yeast undergoes less processing, so the yeast cells experience lower stress and a lower subsequent damage. Being an ingredient used in the production of the major foodstuff, the microbiological quality of yeast is vital. Microbiological quality is carefully controlled and monitored during the manufacturing process, and every batch is tested to the set microbiological criteria. Specifications for baker's yeast require absence of salmonella and other pathogens like Staphylococcus aureus or Listeria, and restrict the number of coliforms organisms to less than 1,000 per gram. So these are the typical values on this patch, and coliforms is a sanitary indicator, and the count levels of coliforms would generally indicate hygienic conditions during production or handling. Lactic acid bacteria are common in the environment and they grow under the same conditions as baker yeast grows. Normal levels of lactic acid bacteria do not cause problem because they occur naturally in the flour in a bakery, and the baker's yeast cells vastly outnumber lactic acid bacteria. Great efforts are made to keep the number of all contaminants to a minimum. However, in the bakery, next to the yeast, also other ingredients sensitive to microbiological contamination are used. Also the hygiene of the dough preparation process and handling of the bread after the baking, for example, during the packaging and transport, is of a high importance to the overall contamination and hygiene of the bread. Fortunately, the baking process kills most of the microorganisms present in the dough, and that includes the yeast cells. So how do we keep the contaminants to minimum during the production, storage, and distribution? These are some of our main controls. It all starts with the pure yeast culture that is propagated under the aseptic conditions in the laboratory to remove a risk of contamination in the early stages of production. Before the molasses can be used for cultivation of yeast, it must be treated to eliminate any contaminating microorganisms or any substances that may inhibit the growth of the yeast or harm its functionality or quality. The molasses is sterilized at high temperatures. and the sterilization of molasses is our critical control point. During the commercial fermentation, the conditions are not strictly aseptic, however, the conditions are kept sanitary. The fermenters are steam sterilized for absolute cleanliness, and since yeast are capable of growth at much lower pH values than most of bacteria, the pH is an important parameter for controlling the growth of contaminants at different stages of yeast fermentation. We also need adequate supply of air, so air which enters the fermentation tanks is filtered in order to minimize potential introduction of airborne contaminants, and processed water, which is required at various stages of yeast production and cleaning, is treated and tested for contaminants on a regular basis. So after the fermentation and separation, the yeast is rapidly cooled and stored in refrigerated storage tanks below 4 degrees Celsius until it is dispatched. So from now on, the maintenance of these low temperatures will be the main measure used to retard the growth of potential undesirable microorganisms and ensure that the fermentative power of the cream yeast is maintained at high and acceptable levels throughout the shelf life. The cream yeast is then transported to the bakeries in insulated tanker trucks, which maintain cream at low temperatures during the whole journey. The stabilized cream is transported in temperature-controlled vehicles. In the bakery, there are two measures that will influence what happens to the yeast during the storage and handling. First is the cleanliness maintenance of the yeast plant, and the second is the maintenance of cold chain, which means keeping the yeast under refrigeration at all times. If the required storage and handling conditions are not adhered to, this could impact on the cream yeast performance and speed up the cream spoilage and shorten the shelf life. To minimize contamination with any undesirable microorganisms, the yeast plant must be cleaned and disinfected after each use. As Mark already explained, the CIP has two cleaning stages. During the first cleaning stage, the detergent will remove visible soils, and during the second cleaning stage, which is sanitizing, this will remove invisible microorganisms. Both stages are very important as both affect the sanitation and subsequent microbial growth in the installation. The CIP cleaning should be validated to ensure that the current cleaning process can remove the microbial and organic residues from the yeast installation to acceptable levels. Since yeast is an excellent nutrient source for bacteria, any deposits of wet or dried yeast on processing equipment surfaces become potential site for contamination. The cleaning should also be verified on a regular basis. ATP swabs, ATP monitoring is a good way to quickly assess the cleanliness of the equipment surfaces as well as the CIP rinse water. ATP hygiene monitoring will aid early detection in increases of microbial or organic matter residues, which will allow you to act early enough and to review the cleaning of the installation if necessary. This will reduce the food source for possible biofilm forming microorganisms. The baker's yeast should be kept at temperatures below 4 degrees, and bulk cream should be gently agitated to keep the yeast homogeneous. The refrigeration between 2 and 4 degrees is also good at retarding the growth of most bacteria that could cause a premature spoiling. So it is important to maintain the cold chain until the point of use. Yeast is a living, breathing organism, and as it ages, it consumes its reserved sugars and becomes less active. This is a natural process. Below 4 degrees Celsius, yeast gas production is negligible. However, if yeast is stored at elevated or fluctuating temperatures for a period of time, it will age faster by accelerating its metabolism, and this will generate heat and further increases yeast metabolism. The warmer the yeast gets, the more difficult it is to cool down again, and this can affect the yeast performance during the shelf life. Yeast condition affects the gas production, gas retention, and potential product flavor. When yeast cells break down, they start to autolyze, and the cell's cytoplasm leaks out into external water, creating a nutritious environment in which other microorganisms can flourish, thus decreasing the yeast shelf life. Autolyzing yeast can also have negative effect on gas retention in the dough. However, if the cream is stored under hygienic conditions at optimal temperatures, it will keep its fermentative power and steady, constant performance until the end of shelf life. The cream will have a minimum 14 days on delivery, and at the end of the shelf life, the loss in activity will be kept to levels which are not detected in use. Finally, I'd like to summarize the Creamiest advantages. Due to less processing steps, the cream yeast has less opportunities to come across potential contamination, and the fully enclosed process adds to this protection. Cream yeast process provides excellent conditions for maintaining the cold chain throughout the supply until the point of use at the mixer. CIP process should make cleaning easier, more systematic, and improve hygiene. No unwrapping, no disposing of packaging, no block cutting, and no manual weighing. Better dispersion of yeast in dough and consistent fermentative performance. So that's all from me, and thank you for listening.
That's great. Thank you very much indeed, Monika, for all of that very, very interesting information. So I think the key thing to remember, actually, these 2 points are key for all types of yeast. To keep the yeast cool at the right conditions, store it in the right conditions, and to maintain hygiene as far as possible when using yeast, but especially when you're dealing with cream yeast systems. So that's all been very interesting. Thank you very much indeed. And it's time for your questions now, but please get in touch with us if you've got any other inquiries about yeast or any other product in our portfolio. You can reach us through our website, which is lesaffre.uk, or you can email any one of us on the email details that you can see on the screen there. So I hope you've enjoyed this presentation. Now let's have a look and see what questions we have. We have a couple in the chat. So, right, here we go then. You can still add your questions if you'd like to, but here are some that we've had sent. First of all, you mentioned stabilized yeast. What does the yeast stabilized with, and does the stabilizer have any effect on the performance of the yeast? I think that's probably one for you, Monika.
Yes, Sara, yes, thank you. The stabilizer is a small amount of gum. It's a xanthan gum, but it can potentially be a gum of a plant or microbial origin, any gum. Its function is to keep the yeast solids in suspension and the cream homogeneous. So there is no need for agitation. The stabilizer can keep the yeast homogeneous for a number of weeks.
Okay.
The influence of GAM on the yeast performance and or gas production capacity, if any, is minimal. It's going to be negligible. The cream is standardized to set fermentation activity as per specification. So as long as the storage and handling conditions are maintained, it should give a constant and good performance throughout the shelf life.
Okay, and does the xanthan need to be labelled on a finished product?
Not on the
The
finished
xanthan
product.
no. Okay.
Yeah, no. It will be labeled on the container because of its function, technical function in the yeast itself, but it does not need to be labeled on the finished product like the bread, because there is no technical function in the final product.
Okay, that's great.
Mm-hmm.
Thank you very much indeed. We have a question here for you, I think, Mark. You were mentioning on the 1,000 kilos liquid yeast system, the ring main, and that the pump on that system means that the yeast can be sent further afield, as it were. And you mentioned a pipe run of 150 meters or so. Does that include the return to the tank?
Well, it really varies. The reason we use a diaphragm pump on the stabilized systems is because the cooling for those systems relies on the cold room in which they're contained. On a standard bulk system, we'd use a much better pump, a bigger pump, a centrifugal pump. So with a stabilized system, we need to keep the heat out of the pipework as much as we possibly can, because we're relying only on the cold room for its chilling aspect. So we use these pumps.
Yeah, I was going to say, so essentially the limit to the pipe run is actually the business about its thermal capacity?
Well, yes, it's about keeping the yeast cold, and therefore using the right pump in order to do that. And the problem with the air-operated diaphragm pump is they don't operate that quickly. You know, you need to go up quite a big size to get the flow rate that we need for cleaning. So that tends to be the limiting factor with a stabilized system. We've had systems that have a general loop of around 200 meters, feeding 4 or 5 mixer points, but it was quite a big pump. As long as you bear in mind that you need to achieve a cleaning rate of 1.5 meters per second through the pipework, then you know, the options are fairly unlimited, really. But it's quite difficult once you're working within that sort of pump range. You know, you are limited in length of pipework, so we have to keep it at a sensible level. So I would say 150 to 200 meters as a circular loop, generally speaking.
Okay, that's great. And while we're talking about cleaning, this is a question I think is probably very pertinent at the moment, with us all thinking about environment and environmental impacts. Is the CIP wastewater harmful to the environment?
It really depends. I mean, if you look at the actual 5 stages that I previously mentioned, the first stage is all fresh water. So you're going to have a little bit of yeast remnant left over. So that's just going to be yeasty water, heavily diluted yeasty water. So that's fine. The next stage would be a caustic, and that's circulated back to the caustic tank. So that's recovered. The third stage is a freshwater rinse, which is also caustic. So you're going to have an element of caustic, an element of slightly alkaline water going to drain, which doesn't really pose that many problems. And then you have a sterilant rinse, which would mean a slightly acidic effluent going to drain, and then you have the final rinse water, which may be recovered. So it's not particularly harmful to the environment. It's just we have to be careful that we don't put too much yeast to the drain. The effluent is usually okay, as long as the timings on the system are right. And when we recover the yeast back to the tank, or when we refill the pipework at the end and start of a ring main clean, as long as the timings are right, we don't put big bursts of yeast to the drain, then there's no real environmental impact.
Oh, that's good to know. That's great to know. Okay. I think we've got time for a couple more questions. Monika, this is one for you. I think you mentioned that the Brueggemann Plus yeast is suitable for short-term freezing of dough. How long is short?
Yeah, about 2 to 3 weeks, I'll say, depending on the recipe and the conditions of freezing. The faster or the blast freezing is less stressing to yeast. So yeah, it just depends on your expectations. So.
Okay, that's great. One more question for you. This is one that's just come in. Are all grades of cream yeast available in the Castalia bag-in-box format? I think the idea behind this is that perhaps if they're making something specific like, oh, I don't know, brioche or panettone or something that needs something osmotolerant, tolerant, you could have that in the bag-in-box while you're using standard yeast for everything else?
Yes, the high active and the medium active are. The freeze tolerant currently is not available in Castalia format. Okay. The freeze tolerant is available in the stabilized containers, I think.
Okay, that's great. I think that's all we have time for now. So if anybody has any further questions they would like to ask, please send them through on an email to one of those contacts there, and we'll make sure that you get an answer. It only remains for me to thank our speakers once again. Thank you, Monika, and thank you to Mark for this very interesting information that you've given to us. And thank you to Gulton for your technical wizardry in getting this all together. We'll be hosting our next webinar in the new year on the subject of live sourdough and its applications. So please keep an eye on your inbox for your invitation to register for that. And on behalf of us all here at the Lesaffre Island, I wish you all a very safe and happy Christmas and best wishes for the new year too. Let's hope to see you at the next webinar. Thanks very much, everybody, and bye for now.
Thank you.
Bye-bye. Bye-bye.